in a chip, there may be a number of flip flops, right? Like I mentioned, it is quite common to have tens of thousands of flip flops, right? And to simplify testing, we build what are called as scan chains, right? An extreme case is when you connect all the flip flops into one single scan chain. That is not desirable because it will take too long to apply tests, right? So in yesterday's class, I told you that one scan testing requires you to scan in values into the entire chain, then capture and then scan out the contents. So it will take 2n plus 1 clock cycles. So n will be very large if you want to connect all the flops into one single scan chain. So it is better to have multiple scan chains. So we may have one scan chain, right, and another one. Okay. So it is common to find 8, 16, 32, right? So these are all scan chains. So each of them has its own scan input and a scan output. Right. The sort of downside of scan testing I may have mentioned to you. One is, there are some disadvantages such as extra area is required, right? All those multiplexers that we end up adding, then extra wires, right? We saw that yesterday. These extra wires, will complicate the, routing, right? So routing becomes complex. Then it also tends to impact the performance of the chip. And we mentioned that there is also an impact on power, right? So scan test power is usually much higher than functional power. And as a result, we have to reduce the scan test frequency. Then extra pins, I may not have mentioned this yesterday. The extra pins are required, right? See here, if you look at this particular chip, if I have inserted 8 scan chains, then I need 8 scan inputs and 8 scan outputs, right? Plus I will need a scan enable signal, right? And sometimes there is a separate scan clock. So you will have quite several extra pins, right? And extra pins usually means package becomes more expensive, right? So package cost will go up. So as a result, you may have to find ways to do what is called as multiplexing. So some functional pins will have to be multiplexed with these test pins, right? So basically, all of this will become part of design for test. Okay, when you are a DFT engineer, you end up, working closely with the design team so that the impact on the design is not, so significant that it is infeasible, right? Any impact on the performance will be, there'll be a lot of resistance, right? People are trying very hard to meet the timing and so on, and if DFT comes and upsets all the timing, etc., so they are not going to be so pleased, right? So DFT engineers have to work very closely with the uh, design team, right? in order to make sure that the impact on area, impact on power, impact on performance, and the multiplexing of pins, all these things they have to take into consideration, right? Then test application time, I think I have mentioned it before. So test application time is also a big concern. The cost of a tester is usually given in how many cents it will cost per second, right? So higher test time means the cost of testing the chip will be high, right? And the other thing is the tester becomes expensive. Okay, so the tester cost is high because, see, think about the tester, what it has to do. It has to store all your patterns, right? And then it has to apply these patterns. Then all the responses will have to be scanned out. You have to compare the good response with the actual response, right? So the amount of storage required in the tester will be high because we have so many patterns, and they have to be brought from the tester at a high speed, right? So which means the tester's memory has to be very fast memory, right? So the testers tend to cost a lot of money because they are built with very high end technology, right? They may use the most the fastest memory technologies will be used in order to build the testers. And see, if you buy a tester, its life is only limited, right? I mean, technologies are frequently changing, right? This was a big deal in the when Moore's law was still going strong. Today, I don't think Moore's law is going so strong, right? We don't see new technologies emerging so soon. But you can think about it. If, let us say, every few years there is a new technology. It used to be 1 year once upon a time, then it became 2 years, and now I think for many years we don't see a new technology. But if you have purchased a tester, which can work for a certain speed, right? And if technologies keep changing, right, then the tester is no more really able to keep pace with the faster chips that are getting manufactured, right? So it will no more be very useful, right? So these are some of the difficulties in scan testing, right? So that is the reason why it sort of makes sense to see if there is a way to include test hardware on the chip. Okay, so that is the basic idea in logic build. BIST stands for built-in self-test. Okay, so built-in self-test. So in a way, what the chip should be capable of doing is, if you give it some suitable trigger, right? If you ask, hey chip, go and test yourself, right? Then after some time it should come back and say whether it is I'm a good chip or a bad chip, right? No need for an AT, no need for AT. So which means the cost will be the cost of AT is all eliminated, right? So this is very attractive. right? Because ATEs, like I told you, cost a lot of money, right? So one will save a lot of money on ATE, but then you will have to introduce a lot more logic on the chip, right, in order to make the chip, self-testing, right? So the amount more logic will have to be included. More logic needs to be included. So which means definitely area will be impacted, and definitely performance will also be impacted, and power will also be impacted, right? But the advantage you get is no tester, and that makes the thing very attractive. A lot of cost is being saved, and if the if you have a tester, but let's say the tester is too slow, right? Then you can't use a tester for the faster chips. But now what has happened is the test logic is on the chip, right? And when you let us say you decide to go and do the same chip in a different technology, right? Then you don't have to do anything new, right? The all the test logic is automatically, sort of getting upgraded to the new technology. So that is another big advantage of logic based, right? So now if you cannot, uh, what was the role of the ATE anyway, right? See, the role of ATE was store patterns, then apply, right? And then read response and compare with the good response, and then declare something is faulty or not faulty, right? This is what the ATE does, right? So if you want to do this by a logic, you may need to do, the first thing is what do you do about patterns? How do you generate patterns, right? And another important thing would be, how do you, uh, you know, how do you compare? Okay. So this part, right? We need to handle something here, and we need to also worry about this. So there are two aspects for logic based, right? So this is, let us look at the first one, right? Namely, generation of patterns. So the traditional logic based has depended on random patterns. Okay. So I would say pseudo random patterns because what is the difference between a pseudo random pattern and a random pattern? A pseudo random pattern is, it depends on the seed, right? So if you specify the seed, then the sequence of random patterns is predictable. Okay. Whereas if you want to generate truly random patterns, then unfortunately every time you start generating the random numbers, you will get a totally different sequence. Okay, that may not be so desirable, right? We want some repeatability. For example, every chip must be, if I am making a million of these chips, then I prefer pseudo random patterns, because I would like to put a seed, and then all the chips are given the same seed, and they will all go through the same sequence of patterns, right? So that is the reason why we prefer pseudo random patterns. So there is a thing called pseudo random pattern generator. Okay, pseudo random pattern generator, which is based on a linear feedback shift register. So let me show you what that looks like. So this is a conventional shift register. Everybody is familiar with the shift register. So if I am willing to feedback some value, see, I can take the output of the shift register and connect it back here. You may have seen these kind of things, like ring oscillators and things like that, right? So here what we are going to do is we are going to take the output of the um, flip flop, the last flip flop, and then we would like to use an XOR gate, and then feed this back. So this is an XOR gate. The symbol for an XOR gate is a plus. Okay. So remember what an XOR gate does. If this is A and this is B, so you may all remember what the XOR gate truth table is. Okay. So you could think of this as an adder, right? So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, but in the modulo 2 arithmetic, it becomes 0. Okay. So we can think of C as A plus B modulo 2. Okay. So that is why we refer to XOR gate as an adder. So in a way, we are adding these two bits. Okay. So the feedback that we are getting is a linear combination of some of the outputs. It's a linear combination because of this addition. I call these as taps. So we in this example we tapped these two outputs. I could tap any of the three. Okay, I could tap all three, or I could tap this and this, or this and this, right? So there are many choices available, right? In this example, I have chosen to tap these two outputs. So let us label these as maybe D1 Q1, D2 Q2, and D3 Q3. So I have taken taps of Q2 and Q3. Now, if you initialize the flops to, let us say, 0, 0, 0, then what will happen is the output of these two flip flops is 0. So the XOR gate will give us 0, right? And as a result, when I clock it, I again go back to 0, 0, 0, right? So if I do this, then the flip flop will remain in the same state. Okay. If I look at Q1, Q2, Q3 as a state, right? So state means this Q1, Q2, Q3. So if I start with 0, 0, 0, I will remain in the same state forever. if I start with anything else, for example, I start with, let us say, 001. So if I have 001, the XOR of 0 and 1 is 1, and that is going to be captured in this flip flop. So I will go into a 1 here, and the other two bits are going to shift. Okay, so I'll get into 100. Okay, so I have gone from 001 to 100. Then if I continue to clock, see the XOR of these two will enter on the left hand side, and the other two bits will shift. So it will go to 010 state. Then the XOR of 1 and 0 will be 1, and the other two bits will shift. Right? The XOR of 0 and 1 is 1, and the other two bits will shift. The XOR of 1 and 0 is 1, and the other two bits will shift. The XOR of 1 and 1 is 0, and the other two bits will shift. The XOR of 1 and 1 is 0, and when I shift, I'll get back 001. Right? So this is the behavior of this flip flop. I'm sorry, this register. Okay, so this is the finite state machine. This is the state diagram. The diagram will depend on what taps I have taken. Okay, the sequence in which I'm going to generate the outputs will all depend on how I have connected all the flip flops and so on. See, there are, if I have n flops, there can be 2 to the power n states, right? So in this example, one of the states, is something that we cannot bring it into this cycle. So it sort of stays all by itself. But the other 7 states it can generate. Okay. So I started with 001, then I went into 100, 010. So it appears like a sort of a random sequence. It appears like a random sequence. So if I take a much larger value of n, suppose I take n equal to, let us say, 32 or something like that, then I may be able to build a large, 32-bit linear feedback shift register, or PRPG, and it will go through 2 to the power 32 minus 1 cycles. So this is a very large number. Okay, and what I put in the beginning, okay, suppose I want to start with 001, that is a seed. I could choose any one of them as a seed. So I could start with 111 as a seed. But once I know the seed, the sequence is deterministic, right? There is no, because I happen to know how they are connected, right? So if I know the connections and if I know the seed, then I can predict the sequence, which is why we call these as pseudo random, right? Usually they label these things as, 1 x, x square, and x cube, which means, you see, this whatever data here is here, it'll appear here after one clock cycle. So in a way, x is like a delay operator, right? Similarly, any data here will appear here after 2 clock cycles, so it's x square, and any data here will appear here after 3 clock cycles, so it is x cube, right? So here what I have done is I have taken tabs from x square and x cube. So sometimes people write this as 1 plus x square plus x cube. Okay. So this is called as the characteristic polynomial of the linear feedback shift register. And that determines, how this behave, how this thing will behave. Okay. In this example, I was lucky and I got all the 7 states. Okay, there are only 8 states in this 3-bit LFSR. So 0, I cannot make it part of the sequence, but I was able to get all the other 7 states. Right. So such a thing is called as a maximal length LFSR. Okay, and the sequence length will be 2 power n minus 1. Okay, and if n is something like 32, you can see that is a very large sequence. I mean, that's a very long sequence. We are unlikely to test with all the 2 to the power n minus 1 patterns when n is like 32, right? Because we may only apply some several thousand patterns. So in this example, I may have a 3-bit LFSR. The input to that is a clock, and I may have the ability to put a seed, right? And after that, I will have 3 bits which are generating some random sequence. Okay, and I could take a 3-bit, a circuit. This is a circuit and a test, okay, which has 3-bit input. For example, we may have taken this particular circuit. So this may be my circuit with 3 inputs. So I may connect them to the output of the LFSR. Then I can throw random patterns, pseudo random patterns, to the input of the combination circuit. See, CUT means circuit and a test. So CUT means circuit and a test. And frankly, it doesn't have to be combination. It could be even a sequential circuit. It doesn't matter. So if you take a, let us say, larger circuit, right? Let us say, a 4-bit or something like that, or 6-bit or 7-bit, right? How do you connect them? These are, there are some well-known polynomials, right? These are published. Okay, you will find it readily in the internet, right? So, for example, if you look for linear feedback shift register, so you will find a Wikipedia page, right? And down, at the end, they have given you all the polynomials up to, let us say, n equal to 24, right? So here, so if you are building a 24-bit LFSR, 24 bit 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 LF This is a polynomial. That means you have to take tabs from 24, 23, 22, and 17. It doesn't mean that this is the only way. Okay. So this will generate 2 to the power 24 minus 1 cycles. So it will generate a max. So this is a maximal length LFSR. Similarly, for 23 bits, it is 23 and 18. Okay. This has been verified by somebody who proposed these polynomials. It doesn't mean that these are the only ones, right? There are other polynomials that will work, right? But it's better to refer to this table than trying your own polynomial, right? It's already done by somebody, right? So you can reuse that information. So in our example, let us say we have x equal to 6. So then we have to take the last two, x sixth and the fifth. If you are building 8, then you have to take 8, 6, 5, and 4. So in our example, if we make this 8 bits, okay, so then this is we have 1, 2, 3, 4, 5, 6, 7, 8. So 8, 6, 5, and 4, I believe, right? So we'll take eighth one, sixth one. There is a shift register, so it has to first have all the shift. So 8, 6, 5, and 4. So we'll need a XOR gate with 4 inputs. And this has to be connected here as an input. Okay. If you try some other combination, then there is a chance that you will get a smaller cycle, which may not be desirable because then your random numbers may repeat again. See, we don't want to apply the same patterns again, right? We would like to apply different patterns. So that is the basic idea of a linear feedback shift register or pseudo random pattern generator. Okay. So we can try this out, okay, as an exercise, right? In Verilog simulation. So please go back to the EDA playground, which you may have used yesterday, or any other Verilog simulator that you are aware of, right? You don't have to use this one. So you are going to build a module. Let us try the LFSR 8. And it requires a clock. It requires a reset, and it produces an 8-bit output. So I have clock as an input, reset as an input, and this will be a 7:0 because I have 8 outputs, okay, and they are registered outputs, okay, because I plan to assign values to Q. It can remember the previous state. So we have described what the inputs are, right? Now we can describe the behavior using an always command. So any sequential logic, we usually depend on the positive edge of the clock or positive edge of the reset, right? So this means wait for either of these things to occur. Either an edge of the clock will appear or an edge of the reset will appear. and priority is given to reset. So we can say if reset has come, then somebody is trying to reset the flop. So we could start by any random state other than 0. Okay. So we could go into, let us say, a seed state, right? So maybe that can also be taken as an input. So we'll put the seed value here. If this is not the case, if we are applying a clock, then the next state, right, will have to be based on that whatever we have written. See, we have to do the characteristic polynomial is 1 plus x per, I think 4, 5, 6, 8. Tabs are 4, 5, 6, and 8. Okay. So for an 8-bit, the tabs are 4, 5, 6, and 8. So the queue, we have labeled them from 7 to 0. Okay. If you want, we can relabel them as 1 to 8. That may make it simple. Okay. Because then the numbers will match. So what we are doing is the queue of 8, right, XORed with queue of 6, XORed with queue of 8654. So that will come as the feedback. Okay. Then everything else will right shift. Okay. So 1 to 7 will be the right shifted values. Okay. Everybody understood this? So we took the feedback bit as the XOR of x8, x6, x5, and x4. And then 1 to 7 has shifted over. So all of this is 1 bit, and these are 7 bits. So together Q is 8 bits. So to test this, we'll have to make a test bench, and we'll have a clock and a reset. Then we may have an 8-bit register called seed, and we may have a 8-bit wire called Q. Then we'll create an instance of LFSR8, which we can call LFSR8. And we have to make the connections. So we'll connect clock main, then reset main, then seed main, and Q main. And then in order to start simulation, we have to write an initial block where we'll start with some seed. So we can start with seed main equal to, let us say we start with 0, 0, 0, 0, 0, 0, 0, 1. So that is our initial state. So it's an 8-bit binary number, which is 0000000. We can clock main can be initialized to 0, and reset main can also be initialized to 0. Right? Then we'll pulse the reset. Okay, by initializing reset main to 1. So we'll, after a delay of 1 unit, we'll make reset main high, and then after one more unit we'll make reset main 0. So we have given a narrow pulse. So this is a rising edge of reset, which will be recognized by LFSR 8, and it will go ahead and initialize its queue, right? And we may want to apply a few clock pulses, right? So maybe we'll repeat this about see, this is 8 bits. Okay, so we may need to apply about 256 clock pulses, right? So the clock pulse will be always see, at the end of 5 units of time, we will at time 0 clock has been made 0, and at time so at this point of time, time is 2. Okay, so clock will become 1 at time 7, right? And again after 5 more units, clock will become 0. So this will happen repeatedly. So we'll get positive edges of the clock at 7, then 17, and so on. And that is when this guy is going to do all this shifting. And then here we could display the queue. So let us go ahead and simulate this. So you can choose this free simulator, right? Then run this. Okay. So these are the states that it is reaching. See, it started with state 1, then it went to 128, 64, etc., etc. Then finally it would have cycled back to 1. Okay. So this is a test of whether your simulation is revealing that it will go through all the states. Okay. So it has finally come back to the state 1. Okay. So this is an 8-bit LFSR. Okay. If you put it in binary, you will know what is happening. If I print the same thing in binary, then you will see the random patterns in binary. Okay. So these are the outputs of the LFSR. These are the random patterns. Any doubts here? So let me look at the chat and see whether anybody has asked any questions. Okay, let me see. Why we generate patterns in LBIST? We can generate in ATPG and we can store this pattern. That is not possible. No? There would be too many patterns, right? We can't store all of them in the chip, right? So that is the reason why we had to do this, right? This doesn't take too much area. See, we are only spending in this example 8 flip-flops, right? Two, 8 flip-flops are able to generate 255 random patterns, right? So as a result, it's much cheaper to do it that way. You can't store all the patterns on the memory. What is the meaning of seed? Seed is the initial value I put in the LFSR. Right? Please repeat polynomial equation. Polynomial equation is, see, if you look at this, see, this is the eighth flop. Okay, so this is labeled like X bar 8. This is X bar 7. See, don't go. There is no equation here. Huh? I mean, this X bar 7 doesn't mean anything, right? There is no, computation involved or anything like that. It is just a way to say the tap number 6 was taken and so on. Okay. So the XOR gate is getting the input from 4, 5, 6, and 8. So the polynomial is written as 1 plus x bar 4 plus x bar 5 plus x bar 6 plus x bar 8. So these numbers indicate what outputs are being tapped. Okay. They use these in communications also, right? If you have taken a course on digital communication, there also you will see that these are called, uh, they are used to generate these CRCs. Okay. So you may have heard about the CRC codes, right? So this is the same thing. All right. What else? How you write 1 plus x2 plus x3? It doesn't mean anything. That 1 plus x square plus x cube doesn't have any meaning. It simply means outputs of the second and third flop are being fed back. Okay, we are not actually, x doesn't have any value, right? How do we validate the test vector's efficiency in determining the types of errors? I don't know what that means. What is the efficiency? There is no term called efficiency, right? If you are referring to fault coverage, you have to do it through simulation. You have to do a fault simulation to find out whether we are getting the coverage that we desire, right? So remember, I mentioned fault coverage, right? At sixth stage, why 1 in 8 position? Where is that? At sixth position, 1 8 means what? See, I have taken the tabs from 4, 5, 6, and 8 and XORed them. And the remaining, see, the flip flops are labeled 1 to 8. So 1 to 7 are being shifted to the right hand side. Right? I hope that is clear. Why plus 1 in polynomial? In this example, it may not make sense, but these polynomials will be used in the theory of the LFSR. You are welcome to read the theory of CRC, right? Where they show that this property of the polynomial is that if the incoming sequence is represented as a generating function, then the polynomial divides the generating function, and the remainder is what is left in the polynomial at the end, and the quotient comes out at the end, right? So don't worry about that one in this example, right? You will need it when you want to see the theory, right? Right now we are not doing that, so don't worry about it. You just assume that it is there. What is dire in log file? What does it mean? Direction in log file. Sixth stage, why 1 in 8 position? See, I don't understand this question. In log file, okay, log file is this. Oh, okay, okay, you are training this. Okay. See, it started with all these ones. So we have taken the XOR of 1 and the other zeros. So that became 1. So 1 came here and all the others shifted. Then again, we had to take the eighth one, sixth one, fifth one, and fourth one. So that happens to be all zero. So it continues like that. I don't know. You may want to do manually a little bit. Let us say the first few you try to do manually, and you'll understand. Right. All I'm doing is I I'm taking the XOR of four of the bits, putting it in the first position, and shifting the remaining. Okay. Is that clear? Any other questions? Okay. So this is how one generates pseudo random patterns, right? And these are fed to the the circuit under test, right? And yeah. Now the circuit under test is going to respond to these uh, random patterns, and it will produce some random outputs, right? I mean, the circuit under test will produce some random data, right? For example, if we took a 3-bit LFSR, then let us say we had put the seed as 001. Okay. Then we'll start with 001 maybe. Then we'll get 100, and then 010. Okay. And this guy is starting, it will produce outputs 000 like that. Okay. So these two zeros will cause this to be zero. So this output is zero. You can verify that the output will be zero, right? The question is, now it's all good, right? To have random patterns coming in, right? But I'm getting all these lot of bits are coming out, right? I can't store these bits, right? For the same reason that I can't store the vectors. In this example, there is only one output, but imagine there is a circuit with a lot of outputs, right? Each one of those outputs will have so many. Suppose I have applied 1,000 random patterns, and I have, let us say, 5 outputs. I'll have 5,000 bits to store. So again, I have not achieved anything if I'm going to use it like that, right? So for that, they use another technique, which is called compaction. So you need to compact all these bits, or I don't know, compress maybe the right word. Compress all these bits into some smaller number, right? See, one simple compressor could be, we could sum all the zeros and ones that we are getting. That could be a simple compression, right? Um, but it may not be a very good compression. So let us understand why that is the case. So here is a LFSR, and it is generating three outputs: 001, then 100, 001, sorry, 0 1 0, right? 0 1 0, then 1 0 1, 1 1 0, then 1 1 1, 0 1 1, then 0 0 1. So imagine that I have taken these first seven vectors: 1 2 3 4 5 6. Okay, this is the first one. 1 2 3 4 5 6 7. And my circuit was that same thing. Let us say AB plus BC plus CA. So for this guy, the output will be 0. For this guy, the output will be 0, 0, 1, 1, 1, 1. So this is what a good circuit will generate, right? If there was a fault on this AB plus BC plus CA, for example, let us say B is stuck at 0. Okay. Then what will happen? The output will be when B is stuck at 0. Then it will end up generating CA, right? So the output will be here. What will happen? CA will be. Let us pretend that this is A, B, and C in this order. So CA will be 0 and 0, right? And 0, and then 1, then 0, then 1, and 0. Okay. So a faulty circuit will produce a different sequence than the good circuit. Okay. Similarly, let us take the output of another one where B is stuck at 1. In which case the answer will be A plus B plus AC, or we could write it as A plus B, right? So this is what this faulty circuit will generate. So here I'll get a 0, here I'll get a 1, and here I'll get a 1, I'll get a 1, 1, 1. So this is what the B stuck at 1 will generate. I don't want to remember 7 bits like this. Instead, I want to compress them in some way. So one way is I can say, look, how many ones are there? I can count the number of ones. So in this case, it will be 2. In this case, it is 6. In the good circuits case, it will be 4. Okay. Now, why is count of the number of ones not such a great thing to use? Because I can't guarantee that there are so many faults, isn't it? There is A stuck at 0, then B stuck at 0, C stuck at 0, etc., etc. And when I simulate all those faulty circuits, right, it is not guaranteed that everything will be different from 4. 4 is what that is the ones count for a good circuit. Okay. But there is maybe another faulty circuit which also produces the same thing. Then unfortunately we have no way to distinguish between a good and the bad circuit. Right? So if that happens, namely the good circuit and the faulty circuit have the same ones count, okay, then we have a, we can't distinguish, right? In this case it's working out well. Okay, so count of the number of ones will work very well here if these are the only faults. But I would, you can, as an exercise, right? So here is an exercise for you. So take this AB plus BC plus CA. and take this OR gate and use the single circuit fault model. You will realize that there are several faults: 1, 2, 3, 4, 5, 6, 7, 8, 9. There are some 18 faults, right? And go ahead and simulate all of them, right? So for example, I have taken a slightly larger circuit, right? I have taken a very large circuit. Let us introduce a suppose I have a 4-bit adder, right? And it takes 3:0 of uh, in A and in B, right? And it produces 7:0 of outside. So we'll not worry about the carry and all that, right? It's just a simple 4 bits, and 4 bits are being added to get an 8-bit sum, right? So we'll assign out sum to, let us say, in A plus in B. So we have an adder. So what we'll do is we'll add one adder called adder 4. That is the name of the adder. Now Q main happens to be a 8-bit wire. So I'm going to connect Q main of 1 to 4 as an input to the first in A, and Q main of 5 to 8 is connected as a second one. And let us take the output sum. Okay, and let us say that is what is the sum. Okay. So everybody understood? What we are doing is we are creating something like this. I took an 8-bit LFSR. It has 8 outputs. So these first 4 I'm giving as the input to an adder. So this is my in A and this is my in B. And it generates one out sum. Okay. So I will print that sum here. Okay, I'll print the sum here. So in A happens to be Q main of 1 to 4. In B happens to be Q main of 5 to 8. And sum is sum. Okay. So then you will get to see how the random patterns are getting generated, right? So 10 plus 1 is 11, 13 plus 0 is 13, etc. etc. Let us write the sum as a binary number. So this is what the good circuit is supposed to do. Okay, this is what the good circuit is supposed to do. Imagine that I will, I figure out how to count the number of ones. Okay, so in every bit position, let us say I have counted the number of ones or something like that, right? Then I can introduce some sort of an error. Okay, I can possibly force, some, right, to have an error. Okay, for example, I could say in a of 3 to 1, but then one of them is 0 always, right? I am forcing a, stuck at 0 fault at one of the inputs. So the fourth, I am ignoring the last significant bit, least significant bit of in a, and I am injecting a fault here. Then you will see that the answers will be incorrect, right? See here, some of the answers will be incorrect. Okay. See, for example, here 15 plus 15 is an even number, but I'm getting something else here, right? Now, once I have this error, right, I can't afford to store these many bits and then declare that there is a fault. I can't go through all these 255 multiplied by 8 bits, right, to see whether there is a. So I could try and come up with some count or something like that, right? But as you can guess, that may not be foolproof. It may cause the good and the faulty circuit to have the same count, like in the example that I gave here, right? So when you do this exercise, right, you can do it in Verilog if you want, right? Simulate the application of the LFSR output shown above to the circuit AB plus. Okay. Then repeat for all faults. Then find the ones count in each case. And see whether there is some other fault for which the number matches. Okay, meaning it also has a 4 as the ones count. If that is the case, then unfortunately we have a situation where we can't tell a good and the faulty circuit apart. Okay, is that clear to everybody? When that happens, we say there is an aliasing. Okay, when the compacted version, see, why am I compacting? Because it is easier to just deal with one compact number like 4, 2 or 6, right? So I have a 3-bit number, right? And it is easier to deal with one 3-bit number than so many bits, right? Here also, see, in this EDA playground, look at the number of bits here. There are too many bits here. If, on the other hand, if I could figure out some way of compacting all these guys into a single 8-bit number, that would be the best. Then I can say, hey, for the good circuit, the pattern should be this, but for the faulty circuit, it's a different pattern. So people have tried many different combinations, and now I think the standard thing to do is what is called as a signature register. So what is a signature register? So in a signature register, we take the outputs coming from that circuit and the test, right? It is producing a sequence of zeros and ones. So I'm assuming that it has only one output. Consider a cut with one output. So I'm throwing random patterns, pseudo random patterns, and this is generating a sequence of zeros and ones. And I will give it to a circuit which looks like this. See, I'll take the same, maybe this register, and I'll take this output coming from the circuit and the test. So in our previous example, the sequence was 0, 0, 0, 1, 1, 1, 1. Okay. A good circuit will produce 0, 0, 0, 1, 1, 1, 1. Right? Here I initialize the circuit to 0, 0, 0. This is my initial state. Now when the 0 comes, 0 XORed with 0 XORed with 0 will be 0. So nothing happens. Right? Then another 0. Then another 0. Then a 1 comes along and that will get into this guy. Then the next one comes along. So XOR of these two and that one will give you 1. Okay, and this one will shift over. Then the XOR of 1 and 0 and the one which is coming in will come here and this will shift over. XOR of these two is 0. That XOR with that 1 will give you 1, 1, 0. Right? So I have 1, 2, 3, 4, 5, 6, 7. I have simulated all the 7 bits, right? There are 7 bits. So no, I started with yeah, I have done all of them. Right? So this 101 is a signature. Okay? So it's a compact form, okay, of this entire bit stream. This bit stream can be any long. It could be thousands of bits long, but the signature will always be 3 bits. So it has taken a very long stream of inputs and compressed it to or compacted it to a 3-bit value. Okay. Now take the same thing and try the other one, namely 0001. Okay, the faulty one, 0001 010. So let us take the initial state was 000. 000 1010. So this was my initial thing. Then the first 3 things will not do anything. Then the next one will cause 100. The next 0 will cause 010. The next one will cause 001. And the next 0 will cause 100. Okay. So you can see that this signature is different from the one which we got here. So this is a good circuit signature. Okay? This is a good circuit signature. This is the signature of the circuit with B stuck at 0. Then you may get another one for B stuck at 1 and so on, right? The There is a small chance. There is a small chance that the good circuit and the faulty circuit have the same signature. Okay, and when that happens, we say it's an aliasing, right? Unfortunately, then the bad circuit will pass, right? We will think it's a good circuit and we'll pass it, right? But if you are willing to take a much larger MISR, this is known as a signature register. Imagine I have taken an 8-bit signature register, right? Then there are 256 possible patterns, right? And only one of them is a good circuit signature. If you are taking an even larger one, let us say 32-bit register, there are 2 to the power 32 patterns, and only one pattern will correspond to a good circuit, and the chance that another faulty pattern will also generate the same signature is very very small, right? So in fact, they argue that it is 1 by 2 to the power n. The probability of aliasing, that means the probability that the good and the faulty signature being the same, is people argue that it is 1 by 2 to the power n. So what is aliasing? Aliasing is when good signature matches the faulty signature. Just like if somebody can fake our signature, right? The bank will not know. The bank tries to do some. They take many signatures from us, right? 3 signatures, and they compare and all that, right? But there is still that small chance that somebody may forge our signature, right? So in this example, the faulty circuit generates the same signature and gets away, right? And the probability of aliasing probability is 1 by 2 power n, where n is the size of the MSR of the signature register. Single input signature register. Okay. So this is a single input signature register. Okay. We can also have a multiple input signature register. So MISR means multiple input signature register. So maybe I can quickly show you the MISR on a Wikipedia or something. Otherwise, I have to write that whole thing. So maybe somebody has given a diagram somewhere, right? Yeah, difficult to understand this. So this is not entirely right. Hmm. This is not bad. So this means a tap. So D0, D1, D2, D3, D4 are taps, right? So if we are taking the tap, it will be like fully connected. Otherwise, it will be left off, right? So that is what they are saying, right? Hey, this is also not good. I don't know what they're trying to do. I'm sorry, this is all. It's not. This is much better. This is serial signature analysis. This is not bad. Not bad. So these are the inputs coming from the circuit under test. So this circuit has, let us say, 8 inputs, D0 to D7, right? And what you see here is the shift register that we have been talking about, right? And this means whether the tap is taken on. I don't know why everybody is writing in such a bad way. It's oof. Let's see which one is the ones there. By the way, Professor Vishwani Agarwal's slides are all generally available easily. You are welcome to look at those. See this one. Okay. So this is what I wanted. So here there is a shift register, right? And D1, D2 are the inputs from a circuit under test. Okay, D1 and D2 are input from a circuit under test, and they are being compressed in this following way, right? So what is being done is uh, the Actually, there are three: D0, D1, and D2. There are three inputs from the circuit in the test. Right? So the last bit, okay, is being XORed with D naught, right? And here, if we have decided to take this step, then we have to take the XOR of the feedback bit and this bit, right? And here we have not taken this step, so only the feedback bit in this one. Okay. So here is how you look at it. The characteristic polynomial is 1 plus x cube. Okay. So what does it mean? We have to take the tab from the first one and the third one. Okay. So this is the first one and this is the third one. So we have taken this tab and we have taken this tab. Okay. Um, so our feedback, right, is XORed with, maybe I'll write it here and try to rewrite this thing. See, let me go back to the same example. I took 1 plus x square plus x cube, right? 1 plus x square plus x cube. So I took this, right? Now I am getting three inputs: D0, D1, and D2, right? So this guy will be XORed with each one of them. And the output, right, is being fed back. Okay, so going back to this guy, okay, let us look at Professor Vishwani Agarwal's slide. Oops. So this output is being XORed with D naught, it is being XORed with D1, it is being XORed with D2, right? And the output of that is being fed back. And see here, it will get XORed with this. And here it will get XORed with this. Okay. So that is an MISR, multiple input signature list. It's an extension of the single input signature list. Okay. So maybe I should cut paste this here and see here he has taken 1 plus x cube. That means the output of the first one and the third one are being taken. Okay, we have taken this output, right? And we have taken this guy. So this is one input D0. This is the second input D1, and this is the third input D2. Okay. So the last stage feedback, right? That is going to get XORed with D2 here. That is also going to get XORed with D1 here. Okay. And it is also getting XORed with D0. Okay. So the feedback is XORed with D0, D1, and D2, right? But because this X is there, right? The output of this is also being XORed. Okay. So that is how you can understand it, right? And you can see that in a multiple input signature register. Okay. So he has taken this example. Okay. Initially, let us say all the flip flops are 0. And he has taken the case where the initial value is 0, 0, 0. So these are the values being produced by this is the initial state. The circuit is producing D0, D1, D2. And these are like this. So initially, let us say 0, 0, 0. Then D0 becomes 1, D1 becomes 1, and D2 becomes 1. Then they are producing 0, 1, 0. Then they are producing 1, 0, 0. They are also producing 0, 1, 0. So these are the inputs coming from the circuit netlist. The MISR, right, is connected like this. This is a 3-bit MISR. Let us say the initial state of the MISR is 0, 0, 0. Now, what is going to happen when I get this 0, 0, 0? Well, it will continue to remain in 0, 0, 0 because this is 0. This is also 0. So this I'll get a 0 XORed with 0, 0 XOR. So nothing will happen. So it will stay in that same state. Next, when they produce 1, 1, 1, say I'll get a 1 here, and the previous state was 0, so I'll get a 1 here, right? Then this had a 0. Now this has produced a 1. So 1 plus 0 plus 0 is also 1. And then this 0 plus 1. So it will go to 1, 1, 1 state. Okay, so now we are in 1, 1, 1 state. Next, the circuit is producing 0, 1, 0. Okay. So this had a 1, 1, and this 0 will produce a 1. Okay. Then this circuit has a 1 here, and it is producing a 1 here. D1 is producing a 1, so 0, and the previous state is also 0, so 1, again a 1 will come. And in the third stage, we will see a 1 XOR with 1, so it will go to 0. And the next state is 1 0 0. Okay, so I get a 1 here, and the last stage has a 0, so 1 will enter here. Okay, and the previous stage is a 1, the last stage is producing a 0. 1 plus 0 plus 0 will be 1 again, right? And the last guy will be the XOR of 0 and 0, so it will also go to 0. It will remain in the same state, right? And so you'll have to repeat this. So please simulate this. I don't know how much time we have. We have 20 more minutes. So we need to simulate this behavior using this, right? So whatever is left in the MISR at the end is the signature. Okay, and if you have a fault in this circuit because of which, let us say D, this became a 1 or something like that, and let us say it's a stuck at one fault, so this also became a 1. So the chance that the same signature will get generated is very low. Is that clear? If you rewrite it like this, I think it will be slightly easier. Let me see if I can rewrite this a little bit. See, we have the flops, and there are some XOR gates here. So the last stage output is going to all of them. Okay, so the last stage output is going to all of them, and the D0 will come here, D1 will come here, and D2 will come here. Okay, and the output of this, because we are taking 1 plus x cube, normally we would have taken the XOR of these two guys. So that is the reason why you see this. And this one, is reading this type. Okay, you know what? See, he has taken the type 2 MISR. That is the problem. Okay, let me explain that to you. This is wrong. Okay. Okay. This may take a couple of minutes. Please bear with me. See, what I described to you is known as the type of LFSR that I described to you. If I have 1 plus x cube, I told you that we have to take these two, right? This is 1, this is x. So x plus x cube is this. So this is known as a type 1, or also sometimes called as Fibonacci LFSR. There is also another one which is called as type 2 LFSR are also called as Galva LFSR. Okay, so Galva LFSR. So there, see, if you see an X here, X bar 1 here, then you have to take the feedback here. Okay, so that is how it works. The last guy comes here, and we'll also have a feedback. So this is the type 2 LFSR. So Professor Vishwani Agarwal has taken a type 2 LFSR, 1 plus x plus x cube, and then he has added these bits, namely T0, D1 and D2. So that will make sense for you. So this is the normal. This XOR gate is for the. I'm sorry. This XOR gate is for taking the this guy and this guy and adding them together and feeding it back. Okay, that was already there. In addition to that, because we are having D0, D1, and D2, we also bring it in here. Okay. And here also you bring it in here, and here also you bring it in. Right. So if you write it like that, maybe it makes more sense. Okay. So my apologies for this rushed thing. So one, so we are taking this output and feeding it here, and we are taking the XOR of these two and feeding it here. And we are doing it here. So this is the original LFSR. Now we have to bring in 3 bits, right? So the first bit we are bringing in here. So we are introducing an XOR gate here. The second bit we are bringing it here. So that will be the XOR of these two guys. So before tying it in here, we'll have to put one XOR gate. We have to take this and connect it to an XOR gate and feed it. Okay, it's very clumsy, I'm sorry. Similarly, we have to take the XOR of this and this. My apologies. So this is the XOR gate, right? And the output is coming here, and there is an D input that is coming here. So this is D1, right? And this output from here is being XORed with D naught. Okay. And the last one is this. So this is your Q naught 1. Okay. So that is the way this. So the whole thing is because we use the type 2 LFSR, right? So type 2 LFSR is like this. Let me give you another example. let us draw the type 2 LFSR for, let us say, x power 5 plus x power 3 plus 1. So 1 plus x cube plus x power 5. So you draw 5 flip-flops. This last one goes here always. Okay. The 3 means, leave 3 flip-flops. Okay. So the third flip-flop, right, is the output that we need to take. So this is 1 plus x cube plus x. So this is the Galva LFSR. So if you this can allow you to compress 5 bits. So if you have D0, D1, D2, D3, and D4, right? So here we have to open the circuit and connect D4 here. Here also we have to open the circuit and connect D2. Here also open the circuit and again open the circuit, connect D1. The last one also, these two are. So this is your 5-bit MISR. We have how many minutes left now? We have, I think, another 8 minutes left, right? So I don't know whether I have enough time to simulate the signature register and show you, right? But what we could have done is we could have taken the output in our example, right? And you could have added an MISR, okay? And that module MISR we have to write here. So the module MISR will take all these things, input clock, reset, and input 1 to 8. Instead of seed, it will take the D inputs. Okay, the D inputs which are coming from the outside world. So again, always at pause edge clock or pause edge reset, right? If it is reset, then the MISR will reset to 0, right? MISR will reset to 0. Oh, I forgot the Q, right? Output reg 1280. Else, see, maybe we can write down one by one. The leftmost one, right? Q1, right? What will Q1 be? It is D1 XORed with Q8, right? So think about it like this. The last guy will come and XOR with the first one. So this is D1 and the last guy is the state bit. Then Q2, we have to write maybe this guy here. Q2 is D2 XORed with Q1, then Q3 is D3 XORed with Q2, and Q4 is D4 XORed with Q3, right? Now, I believe 4, 5, 6, and 8 are special, right? So we have to take the tab, we are taking the tab out of 4, right? So we'll have to, Q5 will have to be, um, we also have to take Q8 XORed with D5 XORed with Q4, okay? Then Q6 is similar. Q8 also needs to be added, that's all. So 4 and 5 we have taken, and 6 also, right? And last but not least, Q8, that is simply equal to Q7 D7 XORed with D8 XORed with Q7. Okay. So we are taking only 4, 5, and 6, right? And 8. So I believe this is how it will work. And now we have to bring that over here. We have to instantiate one copy of the MISR 8. And the input to that MISR 8 will be the sum and clock main, of course, and then reset, I suppose, and the input D will come from sum, and the output will go to signature. Okay. And we can declare signature as a so the sum is 9 bits. Huh? Sum is 9 bits. That's not correct. No, here it is 8 bits. So let us make it 8 bits only. So here we also will display the signature, which is the signature. Okay. So hopefully it will. I'm doing it in a big hurry, so hopefully I'm not made any. So this is how the signature is, right? So it's amazing that we got 0 as a signature in the end. Okay. So we may not apply all the patterns. Okay, we started with 0 as a signature, then we went through some sequence. Suppose we had stopped here. Suppose we decide that enough patterns have been applied here. Where the good circuit signature is 60. Okay, let us do one thing. Let us draw. Let us display this. So let us display that counter here. Okay. So let's go back. Suppose we had decided that 20 is good enough. Okay. So if we had applied 20 patterns, then our signature is 161. Right. Now, on the other hand, imagine that there is a some sort of a bug here, right? Oh, this is a buggy signature. Sorry, I had already introduced the bug. Let me remove the bug now. Okay, this is a good signature, right? And let us repeat it. Okay. So now the signature for the 20th case is something else. Okay, 6, right? So as you can imagine, because there are 8 bits, the chance of another faulty circuit leaving behind the same signature is very low, right? So that is the basic idea behind this signature analysis. So in logic base, to summarize, right? So we need three things. So we need the circuit and the test, right? And the random patterns are applied from this PRPG, and they are compressed using the signature register. So it will be somewhat like this. So we took the signature register here, the multiple input signature register. And we have to simulate for all the faults. Okay, whatever fault list that we have, right? And if there is an aliasing, that means that fault will not be caught. Okay, so that is a loss in fault coverage. Okay, so if there are cases of aliasing, they will result in loss of fault coverage. Okay, so I'm sorry we ran out of time. I would have spent a little more time, but we are already out of time. But I'll be happy to answer the questions that you may have. I'm sure there are some questions waiting. Let us look at the questions. In ATPG, we took weeks of time to read patterns, right? What about Elvist? In ATPG, we took weeks of time to ready patterns. In LBEST, you are not going to generate any patterns. It's all pseudo random patterns, right? So you allow the circuit to generate the patterns yourself. Then see, suppose you are losing coverage. Suppose it turns out that only 90% of the faults are getting covered and 10% are not getting covered. Then there is no other way but to use ATPG to generate test patterns, right? And then those the number of patterns will be much smaller. Okay, then we can have a lower cost ATPG to generate. So it is common to do that, right? So LBIST alone may sometimes not give you 100% coverage, or not even that 98% coverage that you are after. So in that case, that top up, it's called top up coverage. See, whatever the random patterns can give you, go ahead and take it. Then whatever they could not give you, try to use top up coverage with the help of ATPG, right? Can we apply this LFSR to yesterday's shown LFSR? I don't know what is. I didn't show an LFSR yesterday. I don't know. You can, yeah. I mean, I don't know what you mean, but yeah. Can we apply this LFSR to yesterday's shown benchmark circuit? Yeah, yeah, absolutely. I think you meant that S27. Yeah, yeah. Please go ahead. So you can um, take that S27, introduce all the faults, right? And then add maybe there are only 3 flops there. So I think a sort of a single input signature register will be enough. right? You may not need even it has only one output and one scan chain, so you can just simply use a single input register, right? And that will be a good exercise for you, right? So please try to repeat that S27 benchmark. Okay, any other questions? How it know? Okay, seed value is always zero for the MISR. The seed value is always generally zero, right? It doesn't mean that we should not add another different seed, but you know it is the easiest seed that you could add, right? Because it's easy to reset all the flops. Why do you want to complicate it by trying to bring in a new seed or something like that? So keep it simple. Use zero as a seed. Any other questions? Any other questions?
There are no more questions, sir. Thank you so much, sir, for your time. And definitely, I believe all of them have asked multiple questions today. They understood it well. And your
Yeah,
hands-on session will also give them the glimpse of how they can do the same practice for their students, or maybe the students can do the practice related to all these things at their own in the on the EDA playground or similar
sure, sure,
softwares. So
sure.
thank you so much, sir.
Yeah, yeah, yeah. Thank you, ma'am.
Thank you so much for your. Okay, sir. Good night. Gaurav. Hello, everyone. So good night, and let us meet tomorrow 9 a.m. We will be having a lecture by Professor Vineet Sahula. Gaurav, please stop the recording, and if the quiz is completed, then we will publish it later.